In this exercise, we're going to be discussing the constraint tool. The constraint tool is what allows us to apply the constraints to remove the degrees of freedom to lock down the parts. So let's take a look. To start with, top to bottom, left to right here, as always, we have the mate constraint, and it has two different solutions, which I really don't like the way they name this because this is mate and this is mate, or you can go mate flush. So mate mate or mate flush. So usually if I'm telling you to put a mate constraint on something like this will be flush, like this will be mate. If I hit escape here, say I constrain this and this object, as soon as I hit the constraint tool, they snap together. However, if I hit constraint and I turn this on, predict offset and orientation, what that does is that leaves the part where it was. It says, okay, for some reason you want that to be 134.911 millimeters off. Chances are you don't want it to be that odd number, but what I have had happen is if I let it snap together, it could accidentally invert or something. So maybe I do want it to be negative 135 millimeters apart. So if I turn that on, it'll leave them separated and allow me to come in here and tweak it. If I turn this off, it'll automatically snap to itself. Now, one of the things is if you do have this turned on for some reason, don't leave it on because you'll forget about it and then you'll go to put two things together and they won't move and you can't figure out why. So if you need it to be a certain distance apart, toggle that on. If not, toggle it off. Don't need it, don't use it. It is a very helpful tool, but sometimes it can get in your way. The other options with mate, I always tell people to think of mate as gravity. Mate is a really good example of gravity. Take a book or a mouse and you lay it on your desk. You mate those two surfaces together because of gravity. Just because they're mated together doesn't mean they can't move. So we hit OK or apply here. We turn on degrees of freedom. So now you can see they still have X and Y, they just don't have Z. And they can actually rotate about Z, they just can't rotate around the X and Y. So we've removed some degrees of freedom, but we've not removed them all. So let's undo that for a second, because I don't want to lock those together. Not yet anyways. If I come back up here to the constraint tool, the other option with mate is cylinders. I can mate the center line of that cylinder to the center line of that washer, and it'll lock them together. If I hit apply, I'll show you the insert constraint, which works very similarly. If I select the outside face of this and the inside face of my little bushing here, they'll go together. And I'm going to hit OK so I can move it out of my way here. And the difference is these two are locked together and can't move away from each other. If I go back over here to view and I turn on degrees of freedom, I can see that basically they're locked together, but they can rotate. That's all they can do. Whereas if I use the mate to the axis, this can actually slide up and down and spin. So it depends. Do you need to lock it down to the exact spot or let it move up and down? If I were to come in here and do the insert constraint on this, it would lock it to this spot. If I want to remove that, so I can show you what the insert constraint would look like. So insert that ring to that ring. I can still put like an offset in it, but once I do that, that part isn't going to move. It can still rotate like this one, but can't move up and down anymore. The other option you have with the insert constraint, if I select this again, you'll notice I have an arrow here as I go to select it. It'll flip upside down. And basically what that's saying is do you want the two faces to be perpendicular or parallel to each other? Just like mate and flush. So if you ever accidentally grab the wrong side of a bolt or something like that and you see it do this, you can just toggle this around and it'll give you the proper insert. I can do it once more to get this part here. And you'll notice I'm very carefully selecting which face I'm on. I'm really selecting the ring, but I'm selecting the outside ring, not the inside ring. And the reason is because I'm going to select the counterpart to that, which is this outside ring here. If I wanted to select this inside face right here, I would need to select the inside face of my part, because otherwise they wouldn't line up correctly. So I hit apply, and now I have those two faces constrained together. Next we have our little post here. I'm going to use the mate. I'm going to select this little bitty face here. The reason is the smaller the face, the harder it is to select. So if it's out in the open, it's really easy to select. Once I put it inside that part, it's near impossible to select. So I do that little bitty face first, and then I hit apply, and see what'll happen is I can select the inside face of my part real easily right here, and then notice, it basically pretends like that part isn't even there once I select it, because it knows it can't be constrained to itself. So it allows me to go, and I can pick a face over here, whatever, and I can pick that face that's on the inside of that part, and I can hit apply. So now I have one more constraint left to lock this to this, and I'll go back with the insert again. I'll say this hole to this hole, hit apply, and it's saying, hey, wait a minute, this can't be done because it conflicts with another one. So I'm going to say cancel this, and I notice, oh, okay, I've already constrained this part here to something else. Remember we were playing around earlier, and I must have left a constraint on. So I'll go to constraint again, change it back to insert here. So now it flops around there. Next, I have two more constraints. I have the angular constraint. What this allows me to do is I can select this face. I can select this face here. And I can say, hey, I just want these two faces. I don't have any more than that. I could go in and do an undirected angle. Directed angle says, okay, it's going in this direction. Undirected means that I could actually tell it which direction it's going to go. And it doesn't really matter on this one because it's going 90 degrees. But if I was going some odd angle, I could say, okay, this needs to be 45 from this. The explicit reference basically allows you to do a third reference angle on this. I'm not going to go into too much detail on here because this is a basic class and it gets complicated quickly. So I'm going to hit apply. I'm going to select this top face here and this top face here. And I'm going to say, okay, 45 degree angle, whatever I want it to be. It could be 0. It could be 15, whatever I may need it to be. And I hit apply. I have one last constraint on this first page, and it's the tangent constraint. What that's good for is, let's say this was actually rolling inside of here. So I could say this round face onto the side of this. In this case, I'm going to say to the end here, because there's not two flat faces to match together. So I can say this rounded face to this flat face. It would also allow it to basically slide up and down like a bearing or something like that if I wanted it to. And just like the flush and mate, inside, outside, how do you want those two faces to go together? We have two more that I'm not going to go into a whole lot of detail. This is very much a ball bearing or roller slides or something like this where you can actually have motion movements. Then you have transitional, which would be kind of a pipe sliding up and down a square tube or something like that. And then you get into constraint sets where it understands the different sets. Just due to time, we're not going to get into those. We just don't have the time to go through each individual one. So the big things to remember are, do you want mate, mate flush, insert, opposed or aligned, and then angle. Most of the time you're going to do directed angle. And don't forget to set your offset. If you do forget to set your offset, you can come down here and reset it. And then if you do a predict offset and orientation, make sure you turn it off when you get done. When you get done, you should have a part that looks something like this. Don't worry so much about what the angles are, getting them perfect, but you should have something that tells you that, hey, it can't rotate around. You'll notice there's still two free willies in here floating around. And what that is it's this ring here can wrap around this, which doesn't matter, doesn't even have a cutout in it. And then this bushing here can slide around this. Once again, doesn't really matter. Unlike sketch constraints, it doesn't hurt anything if you leave things unconstrained. In fact, the fewer constraints you apply, the better off you are. You don't want to over-constrain stuff. Think about it as in the real world. If you really have a bushing in there that's made to slide, basically meaning that it never locks, then let it never lock. If this was going to be rotational, I could delete this out so that this could rotate around. In the real world, you're not going to lock this down. You're going to let this thing go like this. And the same with my rotation on this. I locked this down to get started, but if I wanted to, I could delete that and free that up. So now I can move my parts around and be able to set my monitor on there and freely rotate it however I want. Most of the time I will, if it is a situation like this, I'll try to lock it down or get it kind of close like that so that I don't have this thing going all willy-nilly on me. Play with it, see what you can do, and see if you can get something close to this, and we'll take a look at assemblies in another lesson. In this exercise, we're going to be discussing mirroring components. We're going to be using the assembly battery pack rev2.iam. So now that we've created our battery packs and we've added our ribs in here, now we need to actually mirror over our little bumpers here to help protect the battery. So what I can do is come up and select mirror, select my component. This could be a subassembly, this could be 100 components, it could be 1,000 components. Inventor doesn't really care. I'm going to select my mirror plane. I'm going to select the plane down the middle. Just like the copy commands, we can tell it to either preview or not preview and reuse standard components. What this actually tells us is if it's a very complex type assembly, you may actually want to turn this off just so that your computer doesn't have to calculate as much. This is very nice. If you have a slower computer or you have a really, really big assembly, you can turn that off just to save you a little bit of overhead. Come up, we're going to say mirror. Now, I'm from a very old school inventor. There used to be some issues with mirror. I have not seen any issues mirroring parts in the last couple releases. It seems to have worked pretty good for me. However, there was some issues at one time with mirroring parts. They didn't work right. There were some CNC issues and things like that. And I just try to avoid mirroring whenever possible. What I do tell people is if it's a simple mirror and we're done, I mirror that over and I'm done with it, then I will mirror this part. If I'm going to have to basically completely change the part anyways, I'll just go ahead and create it from scratch. I may reference in or project in sketches from the other part, the mirrored version of it. But if there's going to be a lot of changes, I just don't really trust the mirror command. Maybe you call this mirror. More than likely, you're going to have like a part numbering system with your name. So it'd be like bumper 1, 2, 3, 4. And the other one would be bumper 1, 2, 3, 5. Right now, we're just going to leave it with the suffix. One thing you do notice is you can turn this off so that it doesn't automatically apply the suffix. You can also tell it to increment. So we can increment it, say, hey, increment it to 2, and apply the suffix. I can tell it not to increment it. You can see I can get all kinds of crazy stuff in here. In this case, I'm just going to call it bumper underscore mirrored. That works fine for me. I'm going to hit OK. So now I have my bumpers in there. Next, I need to mirror it the other direction. So I hit the mirror command. I'm going to come in here. I'm going to select this. I'm going to select this. I'm going to say mirror. If I have a center plane, or for example, I know I have that work plane 1 I can use. Say next. This is going to be mirror 1 of mirror 1. This is going to be the mirror of mirror. I don't like this, but I just want to show you something real quick here. Okay. So now I have those mirrors in there. Now let's talk about this for a second. There's no reason at all to have 4 different parts for this. Yes, we have to have 2. The reason we have to have 2 is because it's flat on one side and it's wedge shaped on the other to be able to get it in there. You don't want to have that situation where you're making 4 separate molds when you can get away with 2. Ideally, we'd make this some kind of symmetrical so you wouldn't even have to worry about it. You just use 1 for everything. So what I'm going to do is I'm going to undo my mirror there. So I have the 2 mirrored. I'm going to come back to the pattern. Go to the circular pattern. I'm going to select my 2 parts. I'm going to select my circular reference. Say it's going to be 2 and 180. Hit OK. So now what you'll notice is I have mirrored this from here to here. And then I did a circular pattern on there. And what that's done is this is the standard. This is the mirror. If you rotate this around, this one over here is actually the mirror and this one's the standard. So now I've reused those same components. At the same time, I've used the mirror command. So I can pattern a mirror and I can mirror a pattern. I wanted to show you that that is a capability in there, that we can do that. So now we've mirrored something and we've patterned it. So like I said, try to watch out for the mirrors and try to limit your mirrors whenever possible. Your mirror is going to create a new part. If this part was exactly the same part, I could actually mirror it and not create a new part. If I just wanted to mirror the location of it for constraints and things like that, what I could do is I could have mirrored these 2 and then just whenever I came up here, told it to reuse them. If these were symmetrical, they would just go up here and it would reuse them. and I wouldn't have to create 2 new parts. We want to keep the part number down as low as possible. The fewer part files you have in your assembly, the smaller your assembly is going to be. You can have hundreds of thousands of occurrences, but if you only have 10 parts, you can run that on like a 286 laptop almost. You can go very low hardware requirements for that. Vice versa, if you get 500 unique parts and no separate multiple occurrences of those, modeled every single bolt and things like that, it's going to run like a pig. So you want to try to be careful about mirroring anything and try to pattern whenever possible. It tends to work out a little bit better for us. Try that, see what you can come up with, and when you get done, save and close. In this exercise, we're going to be discussing calculating the physical properties. Basically, if you come in here and right-click and go to iProperties, click on the Physical tab, you can actually see how much this machine is going to weigh. If I close out of this, and I go into this part, say iProperties, Physical, it tells me that this is 1,500 pounds of steel, basically. It's high strength, low alloy, and all this information. Notice I can't change any of these other than the requested accuracy. Because I'm in an assembly environment, I can't modify that. If I right-click on this and say Open, I can right-click again, go to iProperties, and now I can change from low alloy to carbon to these different densities and have different weights based on that. If you don't change the material type, you will not get the right information. I've seen a lot of people that will take and model everything up and leave it at default, and then they'll be like, oh, the steel doesn't weigh right. Well, it's because you got to tell it that it's steel. It doesn't know how to read your mind and tell that it's steel. So you come in here, you set it to be steel, you hit OK, save it, and go back to the assembly environment. So now your assembly is correct. And you'll notice that I left this cut in half so you can see what the assembly section does to the weight. 56, 125, 669. Come over here to view, and I turn that off. Go back to physical. You'll notice that nothing happened. It's because that assembly section view doesn't actually do anything to the part. It's not actually cutting it in half. It's just turning things on and off. So it still calculates it. If you come in here to a subassembly, you can see how much the subassembly weighs, and so on and so forth, all the way down to the part, of course. If you buy something, so for instance, I come in here and I go to the iProperties of this big roller, it tells me it weighs 25,000 pounds. We buy this roller, and I just modeled it as a solid. Come back over here to my section view again. Just because I'm not going to spend a whole lot of time remodeling something that I'm going to turn around and purchase. But I know that they don't really make these things out of solid steel. They make them out of some kind of layers. They may fill them. They may be hollow. These little shafts like this aren't going to hold a 25,000 pound, 24-inch diameter roller, especially if there's something going through here. So what you need to do is adjust the weight of these rollers to what they actually are. So if you buy something from Grainger or you go out and you order something from somebody else, what you can do is you can come in here and override this inside of the part. So I could say open, go to the iProperties in the part. I don't really care what the material is because I'm not going to model this exactly. Say it's 2,500 pounds according to Grainger. You'll notice right away I get the little hand here. And to me, it looks like somebody's sitting there tapping their fingers. So it tells me that, hey, I've overridden this. This one's calculated. This one's overridden. If for some reason I wanted to get rid of this, I just highlight it and delete it and say update. It'll go back to just being good old-fashioned calculated. But I'm going to override this, say apply, close this out. Now if I come back over here to my machine, look at the properties of it, you'll see that it's saying lost like 40,000 pounds. So it has two of these big rollers on them that were like 50,000 pounds each. No way that that's 50,000 pounds. This thing's 2,500 pounds. So now I get a little bit more accurate. One of the perfect examples of this is I work with a company that designs monitor lifts for TVs and LCD monitors. Well, I'm not going to take the time to model every single little circuit, every single solder, chip, everything inside of that LCD monitor, get the weight just right. Weight's very important to us. So instead of going through all that trouble and modeling this TV or computer monitor exactly, you know what I did? I went and looked at the box. Box tells you right there on it. This computer monitor weighs 12 pounds or whatever it weighs. Come in here and overrode it. And now I can do calculations. I can actually do simulations and see what's going to happen to my lift when I lift it up and down with that. And I can even have it be solid. I can have it be a dumb block. You know, I did make it look a little bit like a computer monitor, but I didn't have to take the time and make it perfectly beveled exactly the way it is, because I just want the generic size and shape of it, and then how much is it going to weigh. Now it tells me here that this is the hand and the calculator, so some of these are real, some of them are overridden. So it's pretty straightforward. You can do a lot with this, and it's very, very accurate. I had one engineer tell me that a design from 1939 was off an inventor because it weighed a different amount. It was 120,000 pound structure. He said it was off by 600 pounds. Now, number one, 600 pounds and 120,000 pound structure, I am fine with that accuracy. If I get it that close, I'm happy. Number two, inventor goes through and does way better job calculating than any engineer can by hand, is it will actually take out the weight of every hole drilled. If you go through and take the time to add the welds, it will add in the weight of all the welds. So you can get really, really close to exactly what your machine's going to weigh by doing this. You can go in and add virtual components. So if you were going to add something to this, say we were going to fill these things up with water. So I could model these without the water. And then I could go through and add a virtual component and know that these things hold, 500 gallons of water, 5 times 8, I could get the exact 8.42 or whatever it is, do the math and put that in there and know exactly how much of those things are going to weigh full of water even. So you could do all kinds of things like that and get your very accurate weights in there. It'll also do the center of gravity. Tell me where the center of gravity is on this machine. If I turn this off here, see the center of gravity, tells me if this is centered or not. Can be very important on some machines, and it is based on that. If I come in here and open this up and override something, for example, I open this up and I override the physical. Instead of this weighing 14 pounds, say it weighs 1,400 pounds. Close it out, save it. Turn off my center of gravity, turn it back on. You can see that my center of gravity moved closer to my part because it's much heavier now. So it moved over. It understands that that thing is heavier and it weighs more. So play with this a little bit. It's really easy to use. It's fun to play with. And it's very, very accurate. It can give you some really good information. Everybody has to deal with weight, whether it's shipping, whether it's safety, whether it's the actual machine design itself, whether it's how much material is going into it. If you're designing plastic parts, very important to know how much plastic's going into it if it's a consumer part, because that plastic gets very expensive very quickly if you're going to add a lot of plastic to it. So play with it, see what you can do, see how much your parts weigh, see how much some of the parts we've already done weighs, and see how accurate it is on something you've designed. If you've built something, let me know how that turned out. I believe you can get some really good information from that properties. In this exercise, we're going to start discussing presenting your assembly drawing. Now, this is one of the lessons that I love to teach, and I really like the fact that I get to teach this one online because it allows you as much time as you want. In the classroom, we have to really limit the time on this, and everybody loves it. This one, your spouse or your boss is going to be really mad at me because you're going to spend days just playing with this because it's so much fun to do. So the first half, we're going to create a presentation view. Most of us know this is an exploded view. So I have this assembly open. I don't necessarily need it open, but I did want to show it to you before I do the presentation view. So I say new, and you notice down here I have a presentation or create an exploded projected view of the assembly. It's a standard IPN. Say create, and you see nothing in there. So I come up and I say create view. And the reason I already had that open is because it highlights it for you. Makes it real easy. You could go out there and say open existing file and track it down and find it. This was created as a metric file, so I'm going to use the metric distances here. I'm going to say 50 millimeters. I think that usually does pretty good. That's about as good as the automatic one does. Usually what I have to do is I start out with the automatic and I start modifying it. I start creating my own. This is super fun and super easy. If it does something crazy and you have a real complex machine, I don't even do the automatic. I'll put it in and I'll tell it, hey, I'm going to manually go through and edit all these. So you can start playing around and seeing what's what. If you expand these out, you see these tweaks. So I can start tweaking it. I can modify the existing tweak here, 50. You notice my lid here didn't go anywhere. So I can say tweak component. Left to right, top to bottom. So I'm going to start over here, and you can see how this is kind of an isolated box. So it's saying, hey, everything on this side, then go to this side. So the first thing it wants is a direction. Direction doesn't necessarily mean that you need to pick on what you're going to be doing. You can come in here, you can pick this little line here. But what I found with this is flat surfaces work the best to give it a direction. So I'm going to go perpendicular to a flat surface. It highlights the Z direction. Now it's asking for the components. Come over here in the browser, or I could select them here. I'm going to select the lid and the gasket. If I just come over in the empty space here, I can start moving this up and down. Or I can come right in here, tweak it, boom, it's where I want it. I hit clear, I can move on to the next one. Say that again. This time I just want the lid, 15 millimeters, and apply. You can see you can do a lot of things and get really creative. Now we're going to add the rotational spin on these. So we're going to say 900 degrees. First thing we pick is the direction, then we select the component. We say we want to spin it 900 degrees. Then you clear, then you select the next one. Select the direction, then the component. Clear. We do that again. So we end up doing that for all 4 screws so that all 4 of them will spin as the lid comes down. This is a really cool effect that a lot of people really like playing with. So you can see you can create a really nice exploded view. Now what we can do with this is we can come in and we can put this on a drawing. A new drawing. Base view. Find the view I want here. And increase the scale. Drop it in there. It's asking me, what am I saving? I'm saving this hydraulic reservoir. And that is in chapter 1. Drops it in, we're good to go. Now I can start doing ballooning. I can do the automated parts list. I'm going to go back and show you the parts list and everything in detail. Here's the 5-6 parts. Come in here and say auto balloon. All these components. Place it around it. And see, I've automatically created this balloon list of everything I need. Now, it may not be in the exact place, and we'll get into details of how to clean that up. But you can see from that, I can create these just wonderful drawings that are good for catalogs. They're good for assembly instructions. They're great for shop floors when you want to show all the internal parts. So you can see these just wonderful way to present your drawing to people and show them how something goes together and show them the inside of something. So take a look at this. It's real powerful. Make an exploded view, get something close to this, and then save this. It's going to be the hydraulic reservoir, 876-5309.IPN. That's what it'll end up saving it out as, and we'll use this in another exercise.